Good morning, students. Today in this session, we discuss about problems on homomorphism. In the last class, we discussed about the definition and the properties of homomorphism. Look at here. Let f from z to z, where z is a group of integers under addition defined by f of x is equal to 3x for all x belongs to z. Examine whether f is homomorphism or not. Let consider x and y belongs to z such that f of x is equal to 3x and f of y is equal to 3y. Consider f of x plus y is equal to 3 of x plus y. Right? This can be written as 3 of x plus y, and 3x plus 3y can be written as 3x is f of x plus f of y. So f of x plus y is equal to f of x plus f of y. Therefore, f is homomorphism. Next, let R plus be the group of positive real numbers under multiplication, R be the group of all real numbers under addition. Then the transformation f from R plus to R defined by f of x is equal to log x to the base 10 for all x belongs to R. Prove that f is a homomorphism. Let x comma y belongs to R plus, considering the two elements from R plus, such that the function is defined like this. Therefore, f of x is equal to log x to the base 10 and f of y is equal to log y to the base 10. Now, f of x, consider f of xy. This can be written as log xy to the base 10 and log x to the base 10 plus log xy to the base 10. Using the property of log, we can split like this. This is f of x and this is f of y. That is, we obtain f of x into y is equal to f of x plus f of y. So, therefore, f is homomorphism. Here, the function is defined from multiplication, the binary operation from multiplication to addition. Therefore, we got like this. F is homomorphism. Let R star, comma dot of all non-zero real numbers is a group under multiplication. Define the mapping f from R star to R star by f of x is equal to 2 power x, comma x belongs to R star. Examine whether f is homomorphism or not. Let x comma y belongs to R star such that f of x is equal to 2 power x and f of y is equal to 2 power y. Right? Consider f of x into y, that is equal to 2 power x y. Obviously, this is not equal to 2 power x into 2 power y. We can't write. Therefore, f of x into y is not equal to f of x into y, f of y. Therefore, f is not homomorphism. These problems we did in the last sessions, but which is under multiplication. It is true for multiplication, but it's it is true for the under the addition binary operation, but it's not true for under the multiplication binary operation. Let z comma plus is a group of all integers under addition. H is equal to 1 comma minus 1 is a group under multiplication. Defining a mapping phi from z to h by phi of n is equal to 1 if n is even integer, minus 1 if n is odd integer. Prove that phi is homomorphism. Consider the two elements from the z. We have to show that phi of m plus n is equal to phi of m into phi of n. Right? Here, the m and n are integers. They are even or odd should be important. Right? So, therefore, consider the case 1. If m and n are both are even integers. If both are even integer, then phi of m is equal to 1 and phi of n is equal to 1. If both are integers means their addition is also even. Addition of the two even number is again even numbers. So, therefore, phi of m plus n is equal to 1. Phi of m plus 1 is equal to 1 means 1 can be written as 1 into 1. 1 can be replaced by phi of m into phi of n. So what we have, phi of m plus n is equal to phi of m into phi of n. We proved this one for m and n both are even integers. Next, if m is even and n is odd, one number is even and one number is odd, even plus odd number, addition of the even plus odd means we have got the odd. Okay, m plus n is odd. So if m plus n is odd, phi of m plus n is minus 1 because the function is defined like this. N is odd integer, then phi of n is equal to minus 1. So here in the place of n, here m plus 1 is there. Phi of m plus n is equal to minus 1. And phi of m is 1 because m is even. And phi of n is equal to odd because phi of n is equal to 1. Phi of m plus 1 is equal to minus 1. And this can be written as 1 into minus 1. This is not a comma. This is just a product. So this can be written as phi of m into phi of n. So we proved The homomorphism for M is even and N is odd. Next, if M and N are odd integers. So in the case of M is even or N is odd, or M is odd and N is even, in this case we have the same result, right? Because M plus N is odd, we got the same. Third one, both are odd, then M plus N is even. Okay, addition of the two odd numbers. Okay, some 7 plus 3, 10. It is a even number. So M plus N is even number. Phi of M plus 1 is equal to 1, right? Even. Phi of M is minus 1. Phi of N is minus 1. Right? Phi of M plus 1 is equal to 1, and that is equal to minus 1 into minus 1, and this can be written as phi of M into phi of N. So in every case of M and N, we have phi is a homomorphism. Therefore, generally phi is homomorphism. Next, let Mn be the group of multiplicative group of non-zero real numbers. Define a mapping phi from Mn of R to R plus for all this phi of A is equal to mod A for all R belongs to Mn of R. Prove that this phi is a homomorphism. Solution. Constrain A comma B belongs to Mn of R, and psi, this one is psi of A is equal to, the function is defined like psi of A is equal to phi for mod A, and psi of B is mod B. So psi of AB can be written as mod AB. This can be separated like this. This is mod A into mod B, right? And this can be written as psi of A into psi of B. This is not a comma, this is what? Product. So therefore psi of AB is equal to psi of A into psi of B. Therefore psi is a homomorphism. Thank you.